Please pause the video and try the problem. Now let's discuss the problem. Here's a summary of the solution for part A of the problem. Let's discuss the solution step by step. Based on the concepts that are mentioned in the problem, we plan to use the Newton's second law problem-solving framework to solve part A of the problem. Part A asks for the speed of mass m1. We can represent this question with the symbol v sub 1. We use the subscript 1 to emphasize that the problem is asking for the speed of object 1. This problem is symbolic rather than numeric. For a symbolic problem, you should write down a list of the given symbols. The symbols m1, m2, and capital R are treated as givens because they're explicitly mentioned in the problem. Little g is also treated as a given because it represents a known physical constant. Write down your list of given symbols. Now we work on the free body diagrams. Usually, we need to draw a free body diagram for each object whose mass is mentioned in the problem. This problem mentions two masses, mass m1 and mass m2. So we plan to apply Newton's second law to mass m1, and we also plan to apply Newton's second law to mass m2. That means we need two free body diagrams. One diagram showing all the forces exerted on mass m1, and a separate free body diagram showing all the forces exerted on mass m2. Mass m1 is moving in a horizontal circle. For concreteness, let's assume that mass m1 is currently located at the far right of its horizontal circle, as we show by the dot in this sketch. Step 1, identify the weight forces. We identify a weight force exerted on mass m1 and a weight force exerted on mass m2. We use subscripts 1 and 2 to distinguish the weight force exerted on object 1 from the weight force exerted on object 2. Now we systematically ask, what is touching mass m1? Well, object 1 is being touched by the table. The table is treated as a surface which exerts a normal force on object 1. There is no friction force because the problem tells us that the table is frictionless. Besides the table, is anything else touching object 1? Yes, object 1 is being touched by the cord. The cord exerts a tension force on object 1. Besides the table and the cord, nothing else is touching object 1, so there are no other forces on object 1. Next, now we ask, what is touching mass m2? Well, object 2 is being touched by the cord, which exerts a tension force on object 2. Notice that we use the subscripts 1 and 2 to distinguish the tension force exerted on object 1 from the tension force exerted on object 2. Besides the cord, nothing else is touching mass 2, so there are no other forces on mass 2. So here is that two-step process that we used to identify all the forces on object 1 and to identify all the forces on object 2. Both weight forces point straight down. The normal force points perpendicular to and away from the surface that is touching the object. So the normal force exerted by the surface of the horizontal table on the object points perpendicular to and away from the surface of the table. So in this case, the normal force points straight up. The tension force points parallel to the cord and away from the object. So the tension force exerted by the cord on object 2 points up. As we've shown with this dot, we are assuming that object 1 is currently located at the far right of its horizontal circle. So the tension force exerted by the cord on object 1 points to the left. Notice that for determining the direction of the tension force on object 1, this sketch of the horizontal circle, which we drew ourselves, turns out to be more useful than this sketch, which was provided by the problem. Next, we work on the force tables. We need two force tables, one force table for mass m1 and another force table for mass m2. In the first row of the force table, we represent the magnitudes of each of the overall force vectors. We use the special formula W equals mg to represent the magnitude of the weight force on object 1 and the magnitude of the weight force on object 2. The problem gives us the symbols m sub 1 and m sub 2 to use for the object's masses. Do not just use the symbol m for the mass. We need to use 1 and 2 subscripts to distinguish mass 1 from mass 2. There is no special formula for the magnitude of the normal force, so we represent the unknown magnitude of the normal force exerted on object 1 with the symbol n, written without an arrow on top. This symbol, T sub 1, written without an arrow on top, stands for the magnitude of the tension force exerted by the cord on object 1. And this symbol, T sub 2, stands for the magnitude of the tension force exerted by the cord on object 2. For a massless cord, the magnitude of the tension force is the same at both ends of the cord, although the direction of the tension force may be different at the two ends of the cord. In introductory physics, we usually assume that a cord is massless, unless the problem indicates otherwise. So, in this problem, the magnitude of the tension force will be the same at both ends of the cord. There is no special formula for the magnitude of a tension force, so we represent the unknown magnitude of the tension force with a symbol. Because the magnitude of the tension force is the same at both ends of the cord, we can use the same symbol, capital T, written without an arrow on top, to stand for the magnitude of the tension force at both ends of the cord. Remember, when we make the standard assumption that the cord is massless, the magnitude of the tension force will be the same at both ends of the cord, so we can use the same symbol for the magnitude of the tension force at both ends of the cord. For purposes of the force table, we do not try to figure out how all these forces will interact with each other. We can let the Newton's second law equations figure out those interactions for us later in our solution. Mass m1 is moving in a circle. For circular motion, you should choose a radial axis that points towards the center of the circle. We're assuming that object 1 is currently located at the far right of the horizontal circle, as we've shown by this dot. So we choose a radial axis that points to the left. In this case, the radial axis will be the x-axis. Notice that for determining the direction of the radial axis, this sketch that we drew for ourselves turned out to be more useful than this sketch that we were given in the problem. Let's also choose a y-axis that points up. In this case, the y-axis will be perpendicular to the horizontal plane of the circle. For this problem, there's no reason why we shouldn't use the same axes for both object 1 and for object 2. We can use this rule to break all of the forces into components. For example, T sub 1 points to the left, which is our positive x direction, so T sub 1x is positive. For another example, T sub 2 points up, which is our positive y direction, so T sub 2y is positive. Remember to include a plus sign for each of the positive components because that will help you to remember to include the crucial negative signs for w sub 1y and w sub 2y. Now we work with the Newton's second law equations. Mass m1 is experiencing forces in both the x and the y components. So for mass m1, I will write the Newton's second law equations for both the x and the y components. Mass m2 is not experiencing any forces in the x component. So for mass m2, I will only write the Newton's second law equation for the y component. Always try to use the exact right symbol, including the exact right subscripts. Notice how we use 1 and 2 subscripts to carefully distinguish the Newton's second law equations for object 1 from the Newton's second law equation for object 2. And we use x and y subscripts to carefully distinguish the Newton's second law equation for the x component from our Newton's second law equations for the y component. For the masses of object 1 and object 2, we use the given symbols, m sub 1 and m sub 2. If an object is motionless in a component, then that component of its acceleration is 0. Mass m1 is motionless in the y component, so we substitute 0 for a sub 1y. Object 2 is completely motionless in both components, so we can substitute 0 for a sub 2y. Object 1 is moving in a circle, so we can apply this formula for object 1. In this case, the x-axis is the radial axis, so the radial component of the acceleration is a sub 1x. For the speed of object 1, we are using the symbol v sub 1. For the radius, we substitute capital R, the symbol we were given in the problem. The radial component of the acceleration points towards the center of the circle, and we've chosen a radial axis that points towards the center of the circle, so the radial component of the acceleration is positive. Substitute the result for a sub 1x, v1 squared divided by capital R, into the Newton's second law x equation for object 1. Remember that the given symbols are m sub 1, m sub 2, capital R, and g. We can treat those symbols as the knowns in our equations. So the unknown symbols are capital T, v sub 1, and n. The Newton's second law x equation for object 1 has two unknowns, capital T and v sub 1, so we will postpone working with this equation. The Newton's second law y equation for object 1 has only one unknown, n, and the Newton's second law y equation for object 2 has only one unknown, capital T. So we will begin by solving this equation for n, and by solving this equation for capital T. We've solved the object 1 Newton's second law y equation for n. However, the symbol n doesn't appear in either of the other two equations, and the problem is not asking us for n, so it turns out that this equation is actually unnecessary for solving this problem. For a horizontal circle, you will typically need to write the Newton's second law equation for the radial component and for the component that is perpendicular to the plane of the circle, but this problem now we see is an exception to that pattern. For object 1, for this problem, we only need the Newton's second law equation for the radial component, the x component. The Newton's second law equation for the component that is perpendicular to the plane of the circle, the y component, turns out not to be necessary for object 1. If it was obvious to you that the Newton's second law y equation for object 1 would not be necessary for this problem, then you don't need to write down that equation in the first place. We've solved the object 2 Newton's second law y equation for capital T, and the symbol capital T also appears in the Newton's second law x equation for object 1. So our next step is to substitute this result for capital T into this equation. Our result for capital T was m sub 2 times g. Now we have substituted that result for capital T into the Newton's second law x equation for object 1. Now this equation has only one unknown remaining, v sub 1. All the other symbols in this equation are on our list of givens. So the next step is to solve this equation for v sub 1. On the right side of the equation, v sub 1 squared is multiplied by the fraction m1 over capital R. The most efficient way to remove the m1 over capital R fraction is to multiply both sides of the equation by the reciprocal, capital R over m1, like this. And here we've obtained our result for v sub 1. Now we can answer the question. V sub 1 equals the square root of m2 times g times capital R over m1. Remember, our answer is required to include only the symbols that are on our list of givens. Well, the symbols m1, m2, g, and capital R are all on our list of givens, so this answer does satisfy that requirement. For example, this would not be an acceptable answer to the problem, even though it is a true equation, because capital T is not on our list of givens. This result is what you get if you solve this equation for v sub 1. Always check to make sure that you've answered all parts of the question. So far we haven't answered all parts of the question. We still need to answer part B. Here's a summary of our solution for part B, and let's discuss this part of the solution step by step. When possible, represent what the question is asking you for with a symbol. Part B is asking us for the period of mass m1. The symbol for the concept of period is capital T. Here's a handout that we introduced in a previous video. There's a link to this handout in the video description box. The handout contains this flowchart, which we can use to convert between concepts that are commonly encountered in circular motion problems. Here's the part of the flowchart that's helpful for this problem. Notice that the concept of period measures the time that is required for the object to travel one complete revolution around the circle. The symbol for the concept of period is capital T. Let's use this part of the flowchart to answer the question. From our work on part A of the problem, we know that v sub 1 equals the square root of m2 times g times capital R over m1. We will use that result for v sub 1 to determine the period. The flowchart tells us that to convert between the speed and the period, we use this formula. The period equals 2 pi times the radius divided by the speed. First, write down the general formula. Then, plug specifics into the formula. For the radius, we substitute the given symbol, capital R. We're trying to determine the period for object 1, so for the speed, we substitute our result for the speed of object 1. So here's our result for capital T. Remember, for uniform circular motion, you can use this formula to convert between linear speed and the period. Remember that this flowchart also shows how to convert back and forth between the concept of linear speed and the concept of angular speed, measured in either units of radians per second or rotations per minute. Now, this expression is an acceptable answer to the problem, but it is possible to simplify the answer, like so. Here are the algebra steps for simplifying the answer. For clarity, I have broken the algebra into many small steps, but if some of these steps were obvious to you, then of course it would be fine to skip or combine some of the steps. If this algebra is difficult for you, remember that most professors would consider it perfectly acceptable to use this expression as your answer to the problem. So here are those two possible ways to write the answer for part B. Remember, our answer is required to include only the symbols that are included on our list of givens. Notice that each of these answers uses only the given symbols, m sub 1, m sub 2, capital R, and little g. So these are both acceptable answers for part B. Now let's check whether our results make sense. For example, we found that capital T equals m2g. Now, m2g is the magnitude of the weight force on object 2. Does it make sense that the magnitude of the tension force equals the magnitude of the weight force on object 2? Well, the problem tells us that object 2 remains motionless. But the weight force on object 2 is trying to begin object 2 moving downward. So to prevent object 2 from beginning to move downwards, the tension force has to cancel the weight force on object 2. So yeah, it makes good sense that the magnitude of the tension force equals the magnitude of the weight force on object 2. Now let's ask whether our result for V1 makes sense. This discussion will build on the material we covered in video 4. So if you skipped video 4, you might also choose to skip this discussion. In our result for V1, m2 is on the top of the fraction and m1 is on the bottom of the fraction. Does that make sense? m2 is on the top of the fraction. This is a positive fraction. That mathematically implies that if we increase m2 while holding the other givens constant, v1 will increase. m1 is on the bottom of the fraction, so if we increase m1 while we hold the other givens constant, that will make the bottom of the fraction bigger. But increasing the bottom of a fraction makes the fraction as a whole get smaller. So, increasing m1 on the bottom of the fraction will decrease v1. So, our result mathematically implies that increasing m2 will make v1 get bigger, while increasing m1 will make v1 get smaller. Do these implications make sense? Suppose we increase m2 while holding the other givens constant. Increasing the mass of object 2 will increase the weight of object 2. Increasing the weight of object 2 will increase the tension in the rope, because the tension force has to cancel out the weight of object 2. Remember that the tension force has the same magnitude at both ends of the rope, so increasing the tension force on object 2 will also increase the tension force on object 1, and the greater tension force on object 1 will provide a greater radial force on object 1. According to Newton's second law, a greater radial force creates a greater radial acceleration. And according to this formula, a greater radial acceleration, holding the radius constant, means that the object must move with greater speed. So yes, it does make sense that increasing m2 will increase v1, just as our result mathematically implies. Remember that the radial acceleration measures how quickly an object is changing its direction of motion. So this part of the logic says that when an object is changing its direction of motion more quickly, the object must also move with greater speed in order to stay on its circular path. How about this result? Does it make sense that increasing m1 will decrease v1? Here is Newton's second law for the radial component. Let's solve this equation for the radial acceleration. That gives us the result that the radial component of the acceleration equals the net radial force divided by the object's mass. Now, let's suppose that we increase m1 while holding the other givens constant. The mass is on the bottom of this fraction. When you make the bottom of a fraction bigger, you make the fraction as a whole smaller. So, if we increase the mass of object 1 while holding the net radial force constant, then the radial acceleration must decrease. According to this equation, decreasing the radial acceleration while holding the radius constant means that the object's speed must also decrease. So yes, it makes good sense that increasing m1 will decrease v1, just as our result mathematically implies. Let's go through that logic again in more intuitive terms. If we increase the mass of object 1, then mass 1 will be more difficult to accelerate. Smaller radial acceleration means that mass 1 is changing its direction of motion more slowly. If it's changing its direction of motion more slowly, then mass 1 must move with less speed in order to maintain its circular path of motion. In video 4, we saw that changing an object's mass can have two potential effects on circular motion. Effect number 1, increasing the object's mass makes the object more difficult to accelerate. That is to say, for circular motion, increasing the object's mass makes it more difficult to change the object's direction of motion sufficiently to maintain its circular path of motion. And Effect number 2. Increasing the object's mass will increase the object's weight. That is to say, increasing the mass will increase the downward pull on the object due to the Earth's gravity. Increasing m1 decreases v1 because of effect number 1. Increasing m2 increases v1 because of effect number 2. Now, in our result for the time period, m1 ended up on the top of the fraction and m2 ended up on the bottom of the fraction. Why does that make sense? Well, you should be able to explain that for yourself. Remember that we just learned that increasing the mass of object 2 increases the speed of object 1, and increasing the mass of object 1 decreases the speed of object 1. If you keep those facts in mind, you should be able to understand why m1 ended up on the top of this fraction and m2 ended up on the bottom of this fraction. Now let's do a recap. It's usually best to apply Newton's second law to each object whose mass is mentioned in the problem. So for this problem, we apply Newton's second law separately to mass m1 and to mass m2. That means that we need 2 separate free body diagrams, one for object 1 and a second for object 2, and we need 2 separate force tables, one for object 1 and one for object 2. The magnitude of the tension force is the same at both ends of a massless cord or rope or string, and in introductory physics, we assume that a rope or a cord is massless unless the problem indicates otherwise. So, in the first row of our force table, we can use the same symbol, capital T, written without an arrow on top, to stand both for the magnitude of the tension force on object 1 and for the magnitude of the tension force on object 2. Always try to use the exact right symbols, including the exact right subscripts. For a multiple object problem, we use subscripts to carefully distinguish the 2 objects from each other. Notice that the problem used 1 and 2 subscripts to distinguish mass 1 from mass 2, and we used 1 and 2 subscripts to distinguish the tension forces on object 1 and object 2, the weight forces on object 1 and object 2, and the Newton's second law equations for object 1 from the Newton's second law equation for object 2. There are no forces on object 2 in the x component. So for object 2, we only need the Newton's second law y equation. Object 2 is motionless, so we can substitute 0 for a sub 2y. Object 1 is moving in a circle, so we can use this formula to find the radial component of the acceleration for object 1. Our radial axis is the x-axis, so this formula gives us a sub 1x. For a horizontal circle, you will typically need to write the Newton's second law equation for the radial component and for the component that is perpendicular to the plane of the circle. But this problem was an exception to that pattern, because for this problem, for object 1, we only needed the Newton's second law equation for the radial component, the x component. It turned out that for this problem, the Newton's second law y equation wasn't actually necessary for solving the problem. For circular motion, the period, capital T, represents the time required for the object to travel 1 complete rotation around the circle. You can use this formula to convert between the linear speed and the period. And here's the complete flowchart for converting between common circular motion concepts. This was a symbolic problem, so we made a list of the given symbols. That list helped us to distinguish between the known and unknown symbols in our equations. Remember that only symbols that are treated as givens should be included in your final answers. Did you find this video to be helpful? If so, you can support the videos by using the PayPal donate button on my website to make either a one-time donation or a monthly pledge. You can visit my website by clicking the link on the screen or by using the link in the video description box. Thank you.